Hello, everybody. We are going to discuss about the End Sem projects which are possible in this course. Okay, uh, so we are having certain problems and their related data sets. Uh, the, we have defined the problems. We have defined three problems as of now, and then but we also allow you to suggest your problems, but only if there is a concrete problem where many people are interested also, means many other groups are also interested, then those can be included, because we plan to have a balanced number of groups over all the problems. One problem could be melody extraction. Let's say, um, if I'm singing, what are the notes I am singing? Audio event detection, in the audio different events happening, like glass breaking or um, gunshot or clapping, or sneezing, and then speaker diarization, who spoke when. We will discuss these problems in detail in the later slides, but for now, uh, I will mention what do you have to do in this whole project. So should pick up one problem, and then you define your goal using advanced ML techniques such as few shot learning, human in the loop learning, etc. We discussed many of these in the first class, and in this class in this session I will be briefly telling about some of them. So you pick up a state of the art paper on these advanced goals. See, the goal is not plain melody extraction or plain audio event detection. No, the goal is not the plain problem solving. You have to define an advanced goal, for example, few shot learning, transfer learning, domain adaptation, etc. The data sets, I have listed certain data sets for each of these problems in the coming slides. You are free to create your data set using those data sets, because for these advanced goals, you need to have slightly modified data sets. You will have certain requirements. For example, if it is domain adaptation, then you need two different domains. So you can create your data sets, your own training set, test set, uh, validation set, using the data sets which I have provided. And if you feel these data sets are inadequate, we can also discuss about having more data sets. Now, you have to submit the problem which you choose and the goal which you choose along with the paper which you want to follow. Uh, you have to submit all of these in MOOCit. We will ask for it when we announce, then you can submit. So, but you can start looking into those things. And we prefer that there are no overlapping of papers across groups. Now, intergroup collaboration is possible because it is so means many of you might not be from signal processing background, so you may need some help for initial feature extraction. So we allow intergroup collaboration amongst you, but only for implementation of basic feature extraction and evaluation codes, because ultimately you have to evaluate your methods. For evaluation, you are computing metrics like accuracy or uh, acceptance rate, false rejection rate, precision recall, etc., etc. So implementation of the codes which are implementing those metrics can be shared amongst groups. We don't mind that, but the main substance should not be plagiarized in any form. And then we will have various reports, or short reports or progress reports, and or presentations along the course to see if you are uh, progressing properly and there is nothing blocking you on the way. Okay, now the assessment can be something like this. So how you define the problem, basically the straightforward problem plus here variant means the goal which you have defined. Yeah, the variant, the goal which you have defined, which could be few short learning or something. So how you define your problem, if you define it very nicely, you get 5 marks. And then we encourage you to use available libraries, not only for feature extraction, but also for implementing some of the machine learning techniques, the straightforward ones. And if you are using libraries to implement the methods, we give 1 mark for per method. Basically, we are encouraging you to explore and use more and more methods. For example, a classifier, you test the accuracy with um, different kinds of classifiers and compare them amongst each other. Um, I would not like that. Okay, you can. I think there is a lot of possibility here, but okay, you are given 1 mark per method. You will have some upper cutoff. For example, if somebody implements 100 methods, no, that is not what we want. Let's say maybe 5 or 6 methods. Up to that, we are allowing. And then how many methods you implement yourself. So for each method you implement, the whole code you write yourself, we will give marks out of 5 per method. There will be some upper limit, maybe 2 or 3 methods. And then the report. So finally, you implement everything. You have to submit your report and you have to submit your codes. For the report, you follow the template of NeurIPS conference, just a template, LaTeX template, which you can follow. And the page limit is 4 pages for the main content, and references can be separately there. And if you have images, etc., you put them in the 4 pages. But we, of course, encourage you to make good diagrams, good images, to make the whole thing better understandable and also quickly understandable. So marks will be given for your writing quality, for your diagrams, how you present your diagrams and figures, and how you present your results, and how you discuss about uh, the work, that how this work is useful, or uh, a critical analysis of different methods, what the methods which you have used, how they compare, and the method, if you have proposed some new method, how it is better than other methods, right? That is very important discussion. And then you submit your codes. For codes, we will be giving marks for readability. If you write properly, document properly, for every function you make proper documentation, commenting, that has marks. And then reproducibility. We will be running your codes and seeing if we are able to reproduce your results. For that, there are marks. And then if you design some new method and you submit your paper to a conference, we give 5 marks as a bonus. Okay. And now what are the possible problems and data sets? One problem, as I told, is melody estimation. So melody means flowing sequence of notes of in an audio. If I'm singing, then the main melody is what notes I'm singing, sa re ga, like that. So and it could be represented in MIDI format or in the frequency in hertz. And there can be 2 types of audio, for example, monophonic and polyphonic. Monophonic means only one source is playing at a particular time. For example, if I am singing, then I am singing. And monophonic audio is very easy to handle because only single source is playing and you are estimating the audio. This is not the goal of the project. Polyphonic audio is a challenging problem. Basically, I am singing and in the background there are many instruments playing. So that is the goal of the project. The problem statement is polyphonic melody estimation. And the approaches could be signal processing approaches, machine learning approaches. So the overall thing looks like this. We have some audio input, and here is your model which will be designing. And the output could be frequency versus time. Means you can give there is a standard format which is. Okay, so the data sets which you can use for this problem, you can use MEAD1K dataset. It is available on this website. And then for reference, you can see, look at this page. This page has got some lot of information. For example, what is the format which you can use for your output, how you represent melody, basically time, the timestamp, and the melody value or the frequency value. So time step and the frequency value, time step and the frequency value, like that. And the time steps are sampled at a sampling rate of I think 10 milliseconds. So basically, after every 10 milliseconds, you are telling what is the current melody or frequency in hertz or in, MIDI units. Now, another project is audio event detection. Uh, this project, you can go through this video by Justin Salomon to see what is audio event detection. Basically, if there are many different kinds of sounds, can you detect them? For example, if I clap, can it detect automatically that the clapping happened here? And you can define your goal. You want to tell only the class which is present, or you want to tell also the timing. For example, when I clap, then it started here, ended here. That goal, this you can define on your own. And then this is another interesting video on how AED has been used for Amazon Alexa. Now, the data sets you can use, there is a famous data set by Google called Audio Set. It's a huge data set. You might not be able to download everything on your computer. So you can use a part of it, because this is a research, this is a project which we are doing. We are not focused on scaling up for huge data, but what we are interested in is you take a small data set and show your method, the effectiveness of your method on a small data. It could be anything, maybe 1 GB or something, that you decide, depending on how much computational resources you have. But the goal is to implement good methods and show how the methods are working. And if they scale up, later, for example, you find that it will scale very well for a larger data set and you want to write a paper for a conference, then later we can also make arrangements for computational resources so that you can work for your paper on a bigger data set later. But for this project, for this course, focus on, you can use smaller data sets also. Then there's a data set called Urban Sound Dataset, which is again open source. I have downloaded it and I have kept it in my drive. You can use it from here. Then the third project could be on speaker diarization, basically process of partitioning an input audio stream into homogeneous segments according to the speaker's identity. So the question we answer here is who spoke when. So it involves both speaker segmentation and speaker clustering. Okay, I will give you an example. So let's say there is a meeting happening, nobody is speaking, then speaker A speaks up, then speaker B speaks up, then speaker A speaks, speaker B speaks, then nobody speaks. And the goal is to segment, so identify, so basically this could be unsupervised or semi-supervised. So you may be given a new set of speakers in the evaluation, which were not there in the training time, right? And so for speaker A, these were the regions where he spoke. We are not telling that who is speaker A. We are not identifying this person, Mr. So and so. But we are just saying, okay, this speech and this speech come from the same person, and that's what we are given. And then this speech and this speech come from another person who is different from this person, and that is the start time, end time, start time, end time. That's it. And then these are audio which we are kind of discarding, or it's not of interest, because even the overlapping, when both are overlapping, that can also be discarded. So this could be a problem, and you define your goals for this problem. So there are many resources available on this website. Diarization datasets, for example. There is this website called Awesome Diarization. They have given good papers, good research, current state-of-the-art research, and also good data sets available. So you can go through these. There are also some open source libraries available for this task. You can use them as well, as I mentioned in the evaluation scheme. Now, what can be the possible goals? This is just a repetition of my first class, but with a few additions. So we have discussed imbalanced data, when little data for certain classes while more for others. Common solution is you do class reweighting in the loss function. In the loss function, you have loss terms for each class, right? And you know the classes which have less samples, you can give more weight so that overall all the classes, they get equal weight. Means each data point gets equal weight over the classes. I hope you get what I mean to say. For example, if some class has got 10 samples, another class has got 100 samples, so the loss function for these 10 samples could be made 10 times for each sample, each of the 10 samples, so that the overall loss function of this class is same as the overall loss function of the other class. That's what I mean. To see how we implement it, this is one. Oh, not this. Okay, maybe in the next slide I will show you the paper where I have implemented this. And then another common solution is generating synthetic samples for classes with little data. These are some common solutions, and you can start from here as a baseline. And then there are good references like Learning to Model the Tail. This is a paper in NeurIPS 2017, which you can use. And, this is one of my papers where deep embeddings for rare audio event detection with imbalanced data. So I use some kind of embedding approach to improve the training. And then this is another paper, but you are free. You feel free to find your own papers as well. Then next problem could be learning from less data. Like you have, let's say, if I give you lots of speech data from America, American speech, English American speech, but now there is a speaker who is Indian and he speaks English. So can you learn from the American data? Can you leverage the American data to train for this speaker, because or train for Indian speakers? So there might be very less data from this domain, but your let's say for this new speaker there might be very less data for training, but you leverage the knowledge from other speakers and transfer to here. So you can use few shot learning, zero shot learning, domain adaptation, etc. And there can be also other problems like, for example, you have some new classes. For example, you are doing audio event detection for certain classes like clapping and sneezing. And suddenly there's a new class called cuffing in the target domain. So there's source domain, target domain. In the target domain, you have a new class called cuffing. Then how you can learn from very less samples of cuffing, you can improve the performance on this new class. So these all problems can be are possible. So you find a suitable paper and you can work on it. Then interactive learning, basically this is like, for example, you got a new class called cuffing, and now the human is helping the machine to learn. For example, you found that, okay, results are very good for, in the training time, results are very good for sneezing and clapping because we had training data for that. But for cuffing, the machine is not doing very well. So human is giving certain labels. Okay, this is a cuff, this is a cuff. And from that input, the machine has learned and it improved the performance over all the classes. And then in the second iteration, again, the human gave 2-3 more labels. And then again, the machine learned, the performance improved. So human is giving more and more inputs, machine is improving and improving. So it's a kind of interactive learning with a human in the loop. So you can define your goal like this, very interesting goal, and there are good papers on this which you can consider. There is a blog you can read through. And then we could have active learning. The machine asks the human annotators, I am uncertain, can you please label this for me? So how you quantify uncertainty. There are some good papers recently. Maybe I will share with you later, or you can ask me for those papers. So this is from Jeremiah, I think. Jeremiah from Google, that how your machine is not only outputting the labels, but also uncertainty values associated with that label, and everything is trained end to end. Very interesting work. If you want to do it, then you can go to Jeremiah in Google has this paper. I can share that later with you. Then another goal could be fairness in AI. So algorithms or models could be biased. So good results for males, for example, not so good for females because more male training data. So fairness is important in decision-making systems. So how do you incorporate fairness? And this could be another goal. And then anomaly detection. How do you detect anomalies in the data? So we are not telling you what kind of mistakes are possible, but just that, okay, certain, if you find some anomalous behavior, then you can do it. So then explainable AI. So can your classifier also explain why it made that decision? So you can work in this direction as well.